fixed ROI box. The slide over the entire image. While slide over the entire image, we have our own specifications, like how many pixels you wanted to overlap. Okay, according to your experimentation, you can design it. In our coding also, we are going to fix this. Whether the sliding window you wanted to move after every 20 pixels, if you wanted to slide, or every 10 pixels, or every 30 pixels, or every 50 pixels in a finer moment, or you need a coarse look, that you can define. So I'm going to slide this box. Okay, I'm going to slide this box over the entire image like this. Every time I'm going to keep this box over the region. Okay, first my box is over the top left corner like this. Next position is the red. The next position is the black like this, isn't it? So what I'm going to use is a very simple logic. Look at this. This box, I'm going to ask my pre-trained model. Okay, do you notice any object known to you? Because you have been trained to taught so popular objects like 1,000 classes, you have been trained, right? Naturally available objects in our environment. Whether this box looks familiar to any of the earlier objects you have seen earlier, whether it looks like a tree, or it looks like a car, or a person, or a cat, or what, or aeroplane, or what. So every box, the same rule. Before you present this bounding box to the pre-trained model, remember to reshape it to the standard size. This will understand. Okay, so what we call this the warping. Image will be warped and it will be asked over this. So the next sliding window will be asking this: is there any object? Is there any object? Throughout the entire image, each and every boxes will be asked. In that manner, when the sliding window, once it covers this portion, in the same way, row wise also you shift. Again, this also can be, we can describe how many rows you are going to shift rightwards and how many pixels you are going to push downwards. And you are going to keep ask the entire boxes. Comparatively, the sliding window will be far less when compared to 2K proposals. Okay, instead of 2K proposals, you will get hardly less than 1,000. Window will be there. When the sliding window is coming over here on this objects, and it's quite natural process that the sliding window sometimes it will partially cover this, and then it's the next position is completely cover this. Again, also it's partially cover this. Now for the same object, this window will give me the person with 0.6 probability, perfectly covers with 9% probability. After crossing the person, it says 0.4 probability. Then it is covering the car region. So it gives the car region with the probability of 0.6. And when it perfectly covers the entire car, it gives maybe 0.8 or 0.9. So we'll be using a technique called non-max suppressor, class-wise, per class, because it is a man class. Out of the same bounding box, okay, it's going to be overlapped over the same object again and again. We don't get a single bounding box, because when you keep on moving, sliding over the image, this box also tells there is a man. This box also tells there is a man. This box also tells there is a man. But look at the probability scores of it. What this NMS algorithm is going to do, non-max suppressor. Non-max suppressor. Nothing complex about this algorithm. It's a very simple idea. It is going to non-max, whichever is a non-max out of these three, 0.6 is not a max, 0.4 is not a max, only 0.9 is a max, right? Out of these cases. It is going to suppress, that means opposite is, it is going to keep the max and it is going to suppress the non-max. That is the idea. So it is going to keep the maximum probability per class wise it will do. Similarly, for the car class, it is going to do, even though multiple sliding windows are over this car object, it is going to keep one bounding box which has the highest probability score. That alone is going to retain. You don't need to manually do any logic to do this. So we have a package is part of our Python layer, Keras layer. Just import this non-max suppressor and just pass the bounding boxes, class-wise bounding boxes to us. So that means one bounding box per class you are meant to get. But there is a difficulty where there is a challenge in this approach. Of course, apart from the computational complexity, there is an issue in this approach. Can you tell me a drawback in this? What is the challenge apart from the computational challenges?
Fixed ROI. We need to increase ROI for bigger objects.
Yeah. So here the limitation is a fixed ROI. Rather, changing the ROI, because the changing the ROI came a later period of time, I'll tell you. Okay. What the OverFeat paper proposed, the researchers proposed the idea here is, sometimes see the same person, when the same person is closer to the frame, when the person is closer to the frame, it is a very big, and if the person is very small, what happens? Suppose your sliding window, you are applying the fixed size like this. With the sliding window will not cover the person with a decent score. We are expecting at least 80 or 90%, right? But this box will tell the probability of a person because only partial features are there. Maybe it says 0.65. But the same person in a forever distance, maybe it will, this window will cover this person. But very closer to the frame, it may not cover. Same thing applicable to the car also. If the object correctly matches with my sliding window area, it will perfectly recognize. Otherwise, it will partially. To overcome this process, what was the idea proposed by the researchers? Proposed the OverFeat paper. They proposed image pyramid technique. What they have done, the same image, okay, they scaled to different sizes. Instead of changing the bounding box, they changed the image size. So as per the paper, they have demonstrated 6 standard dimensions. Okay, as an implementation, we can have our own liberty to define a number of pyramids according to the computational limitations. We can modify that. So in the afternoon, we'll see in the coding which part of the coding we can modify. So the same picture is represented as this dimension, another dimension like this, another dimension. As per the paper, there are six standard scales. They have downsized it, and across the scales, see, for example, in this, the person is very closer to the frame. Okay, and in the scaled version, now this is my fixed bounding box, isn't it? Across the scales also, my probability scores will be retained, not only based on this is done for one single frame, isn't it? Same operation is being performed across all the scales. Your NMS is going to work. Your NMS is going to work class-wise, not on single scale, but on the multiple scales. So your NMS is going to see that, okay, in the scales also, it is going to it has seen that the bounding boxes, it is covered my object like this, then it is covered the object like this. So we have some 3 scores like this, 0.6, 0.7, and 0.56 like this. And in the scales also, you have multiple overlaps will be there. But across the scales, when we overall, your NMS is going to pick the best score is going to pick in this scale, isn't it? So the best score, maybe 0.9 is the best score. Here also maybe 0.56, 0.8, and maybe 0.72 like this. So in the scales, it is going to pick the max. So the best score, which is it is captured in the scale. Okay. Again, as usual, whatever the coordinates, because we only operate the bounding box, isn't it? So we know exactly every movement, every position, you are asking, hey, this bounding box, you are passing to the pre-trained model, you are asking you what is the person inside this, what is the object inside this. We are asking the pre-trained model, right? Since we only asking the model, actually I know how I can ask the model. By knowing the coordinate only, I can ask the model, right? So in this x0, y0, x1, y1, what is the object? Okay, in the next position of x0, y0, x1, y1, what is the object? So basically, I know the coordinates also. So the beauty here is I no need to separately train any bounding box regressor to understand the coordinate. Naturally, my control, I have the control of operating the bounding box. I know which location I'm operating. So at this location, I'm getting the maximum probability. I can retain this coordinate x0, y0, x1, y1 coordinate. For this x0, y0, x1, y1 coordinate, I got the maximum probability. So you can do the reverse scaling according to what dimension it is being scaled. That is being, we can take care in that our coding. The reverse scaling, we can do it according to the scale wise, the scaling. In this scale, what is the reverse mapping? At this scale, what is the reverse mapping? At this scale, what is the reverse mapping? So this is the idea of the image pyramid, sliding window and image pyramid, the idea proposed by the OverFeat paper researchers. It's a modified version of the practical version of RCN. What they have done is they just replaced the region proposal idea. Instead of this also proposing the regions, but comparatively less number of regions it proposes. According to the size of ROI, if you keep your ROI is very small, it is going to propose more regions. On the other hand, if you keep your ROI is bit larger, it's going to propose less regions. So to overcome the problem of whether my object is covering a small object, okay, a small object, sorry, my small window covering the big object, right? So my small window is not able to cover the big object because my object is very close to the frame. So a bigger object is very well captured in this case, isn't it? So similarly, whether your object is a small or a bigger, a particular scale, it will be captured. So no, we don't have an issue of whether my object is bigger than the ROI or a smaller, very small in the ROI. Maybe your object is very small. Say, for example, for this bounding box, there is a farthest, there is one object is very small, a very small object, but your fixed size is this. So even though this is not a perfect ROI, this is not a perfect bounding box for a smaller object, right? Of course, we were not happy with the score, the probability score of this. This object is not being, because in the background pixels are giving features which is not related to this object, right? Some background features will be there. In the background, maybe some trees, some other background, some pixel values are there, which is not part of this object. Imagine some faraway place, there is a dog standing in the road, right? So apart from the dog, there is some trees, okay, some other objects also there. So it is not clearly gives, this bounding box is not going to give a clear representation of the features of only dog. Apart from that, my background portion also. So my model may not give, maybe it says dog, okay, dog with a probability, very poor probability score, 0.46. But the same dog pictures in some other scale, bigger scale, it will occupy more, more space, the same size ROI, it is going to cover the dog in a expand scale, right? A smaller object can be very well captured in the higher scale image, and similarly the bigger image are very well captured in the low scale image. That's an idea here. So that is an image pyramid, and followed by the sliding window technique. This idea can be easily carried out.